So here we continue with different types of formulas and ways that we can rewrite trig expressions. The power reducing formulas are actually pretty important, especially when you get to Calc 2 and you do a lot of the trig integration. We reach back and rely on these power reducing formulas because we can't integrate like a cosine squared or a sine squared directly. But boy, if we could change it into a double angle formula, then it works a whole lot better. So there's times when we only want to work with first degree powers. So if you go back to those cosine 2 theta formulas and you try solving for other variables, like look at the first one. I've got the cosine of 2 theta equals 1 minus 2 sine squared theta. If you solve that for sine squared, you would do what? You would subtract a 1 from both sides, and so you'd get cosine of 2 theta minus 1 equals negative 2 sine squared theta. And then divide everything through by negative 2. Well, dividing by negative 2 switches this around up here, right? It becomes a 1 minus cosine of 2 theta over 2 equals sine squared theta. So by doing that, we no longer have a squared term. We do have a cosine of 2 theta, but cosine of 2 theta is first degree, and that's nice. If we do the same thing over here, we add a 1 to both sides. We get cosine of 2 theta plus 1 equals 2 cosine squared theta, and then we divide by 2. And usually we just switch the order of the first one around. Doesn't matter. We could write cosine 2 theta plus 1, but oftentimes we write it as 1 plus cosine of 2 theta over 2 equals cosine squared theta. And so committing these formulas to memory is important, because, like I said, in successive math classes, you actually will use this quite a bit. Silly little way to remember things. The sine squared has the minus sign in the middle, and sine and subtract start with the same letter. And you'll think that's the stupidest thing until you're sitting there on a test going, is the sine squared the 1 minus or the 1 plus? Oh, sine is subtract, so 1 minus cosine 2 theta over 2. And again, the other thing, too, you realize is they both have two cosine of 2 thetas. There's not one having sine and one having cosine, although there are other reduction formulas that use sines, but let's stick with these. And then if you want tan squared, just take sine and divide it by cosine. So you'll end up with a 1 minus cosine of 2 theta, that's your sine squared theta, 1 plus cosine of 2 theta, that's your cosine squared, so sine squared over cosine squared is tan squared. All right, and those formulas are reflected on this slide over here. In the formula sheet, you'll have tan squared, but you won't have sine squared and cosine squared. But if you're quick enough, maybe you realize that this is the sine squared part, and that's the cosine squared part, so just take it and divide it by 2. And look, the formulas have arrived in the strangest ways. What are we going to do with this? Not a whole lot right now because we're not in Calc 2 yet. But we can work on rewriting trig expressions, and that's part of what pre-calc is, right? You're doing the foundation work for what you're going to do in successive courses. So the question says, write a trig expression for cosine to the fourth that does not contain trig functions greater, or powers of trig functions greater than 1. So cosine to the fourth, the very first thing is, well, I don't have a formula for cosine to the fourth. Oh, but I do have a cosine squared formula. So what if I thought of cosine to the fourth as cosine squared times cosine squared? And then I replace that cosine squared with a 1 plus cosine 2 theta over 2. So that's the first cosine squared. That's the second cosine squared. And then I can pull out what? Well, 2 times 2 is 4. So let's pull out the quarter, and I'm left with the two numerators, the 1 plus cosine 2 theta and the 1 plus cosine 2 theta. So just to save a little space, let's combine these things now. So let's multiply. I've already pulled the 4 out, right? 2 times 2 is 4. So let's FOIL those things out. 1 times 1 is 1, plus a cosine of 2 theta, plus a cosine of 2 theta. So a cosine of 2 theta and a cosine of 2 theta is 2 cosine 2 thetas. Now when you multiply cosine of 2 theta times cosine of 2 theta, you get cosine squared of 2 theta. Well, hold on a minute here. I thought we were trying to get rid of those higher power terms, and yet when we work through the formula, we still have one. But the nice thing is we have a cosine squared instead of a cosine to the fourth. So let's think for a minute what I'm going to do with a cosine squared of 2 theta. I know that cosine squared theta equals 1 plus cosine of 2 theta over 2. So what if I went ahead and replaced that theta with a 2 theta? Because it looks like that formula is asking me to do that. Take that theta and replace it with a 2 theta. Well, if I replace that theta with a 2 theta, I replace this theta with a 2 theta. So now I have cosine squared of 2 theta equals 1 plus cosine of 2 times 2 theta is 4 theta over 2. And that's what's going to happen here. I'm going to replace this thing with a 1 plus cosine of 4 theta over 2. Except when I do that, instead of putting the whole thing over 2, I'm going to separate it like that. And I'll show you why in a minute. So let's copy down what I already have. 1 plus cosine 2 theta plus, and then that cosine squared 2 theta becomes a 1 plus cosine 4 theta over 2, which I split into 2 pieces. Why did I do that? Because I can take this 1 and this 1/2 and combine them. 1 plus 1/2 is 2 halves plus 1/2, which is 3 halves. So here I'm going to carry this up to the next column. The quarter stays on the outside. 1 plus 1/2 is 3 halves, plus 2 cosine 2 theta, plus, instead of writing cosine of 4 theta over 2, I'm going to write it as 1/2 cosine 4 theta. And then my last step is just to distribute the quarter. So a quarter times 3 halves is 3/8. A quarter times 2 is a half, right? 2 quarters is a half, so I get a half cosine of 2 theta. And then a quarter times a half is an eighth, so I get an eighth cosine of 4 theta. That's my answer. I have successfully written cosine to the 4th power as a trig expression that does not contain trig functions, powers of trig functions greater than 1. And again, it'll have cosines of 2 thetas, it'll have cosines of 4 thetas, but it won't have anything squared in it. And that's what's important here. All right, can we do that for sine to the 4th? Maybe it's just a good thing to see how these things work out. Expression for sine to the 4th that does not contain powers of trig functions that are greater than 1. Same idea, right? We'll write sine to the 4th as sine squared times sine squared. And if you think you have the idea of it, you could probably zip through this thing. I think it's just nice to go through a second example of this. So sine squared, remember, is the 1 minus cosine 2x over 2. So I'm going to get 1 minus cosine 2x over 2. That's the first sine squared. The second sine squared, again, is 1 minus cosine 2x over 2. 2 times 2 is 4, so I'll pull out the 4. Foil the 1 minus cosine times 1 minus cosine, and I get 1 minus 2 cosine of 2x plus cosine squared of 2x. Again, I'll remind myself that if cosine x, or cosine squared x, equals 1 plus cosine 2x over 2, then cosine squared of 2x is going to be 1 plus cosine of 2 times 2x, in other words, 4x over 2. So I carry down my 1 minus 2 cosine 2x, and then I replace that cosine squared of 2x with a 1 plus cosine 4x over 2. But I'm going to use the same trick that I did in the last one, which is, instead of putting them all over 2, separate them into 2 parts. All right, just like last time, the 1, there should be a plus here, 1 plus 1/2 is 3/2. So I get 1/4 times 3/2 minus 2 cosine 2x plus 1/2 cosine of 4x. So multiply through the 1/4, and I get 3/8 minus 2/4 is 1/2. 1/4 times 1/2 is 1/8. And there's my answer, which looks suspiciously like the last one. Right? What's the difference between them? Well, besides the fact that I changed my variable partway through, I should have left this as x's instead of thetas. The only difference is actually that sign before the cosine of 2x, right? Is the negative half for sine, is the positive half for cosine. Other than that, the rest of the function remains the same. So you're going to get very similar looking answers to these things. But it is worth running through the algebra that goes with it. Just be aware of how the algebra works. Like, don't make silly mistakes or, combine things incorrectly. And you'll have ways to rewrite these expressions. And then, like I said, when you get to higher level courses, you'll be able to use them. All right, let's knock out the last little bit from this section. This is a combined 5-2, 5-3. So half angle formulas. All right, they're not used nearly as often. You're not expected to memorize them, but they allow us to find exact values for additional angle measures. So what you do is you take the power reducing formulas and replace the thetas with these things that are called alphas, alpha over 2. They look like little fishies, but they're alphas. They're the first letter of the Greek alphabet. And you take the square root of both sides, you get the half angle formulas. Now, each of the formulas has a plus minus on the outside, which is there not to tell you that they're both answers, is to remind you to check the quadrant where the half angle is to figure out if it's positive or negative. So, are you ready for these half angle formulas? And again, we're not memorizing these things. We're just using them. So it says sine of alpha over 2 plus minus the root of 1 minus cosine alpha all over 2. Your cosine is going to be the same thing with a plus instead of a minus. The tangent is going to be the division of them. And then there's also two other ways to write the tan of alpha over 2 involving 1 minus cosines and 1 plus cosines. Okay, so how do we do this? I have an example already worked out, and you'll see it in the PowerPoint too. So here we go. Suppose you want to find an exact value for the sine of 105. Well, does this mean that the half angle formula is the only way to do this? No, I have a funny feeling we already did this with one of the other sum and difference formulas, right? Because isn't 105 degrees 60 and 45? So I could have done it with a sum formula, right? I could have done it with the sine of 60 plus 45 and worked it out that way. But here's another way to do it. The half angle formula as the sine of 210 divided by 2 will also work. So my formula that I'm going to use for the sine of 105 is what? The sine of alpha over 2 is 1 minus cosine alpha over 2. So it's the square root of 1 minus cosine alpha all over 2. So the cosine of 210 is negative square root of 3 over 2. So I do 1 minus cosine 210 all over 2. Now, when I go to run this through, how do I calculate 1 minus a negative square root of 3 over 2? I've got to turn this 1 into a 2 over 2. So now that's where I get a 2 plus the square root of 3 on the top and a 2 on the bottom. Well, now I got a mess and a half, right? I got a square root with a square root inside of that square root and a fraction. So the top is divided by 2 divided by 2. So let's take the divided by 2 divided by 2 and make it divided by 4. The next thing I can do is think of this as the square root of 1/4 times the square root of 2 plus root 3. The square root of a quarter is a half. So the half comes outside the radical here, and I'm left with 2 plus root 3. What that means is, yes, I have a radical inside a radical, and that's okay. These formulas sometimes come up with funky-looking answers. Then I need to figure out whether I want a plus or minus. So the sine of 105, where's 105? Well, this is 90, so 105 is over here somewhere. Second quadrant, sine is positive, so I'm going to use the plus version. So I don't have to write anything. It's just this. Here's my answer. That's how you find the exact value for the sine of 105. Now notice if I did it with the sine formula like sine of 60 plus 45, I wouldn't have something that looks like that. That's okay. You'll see multiple different ways to write something that has the same numerical value. All right, so we're not going to do a lot with the half angles. Let's try one of these. So the sine of theta over 2. Biggest misconception is if you want the sine of theta over 2, you can find the sine of theta and divide it by 2. That's not the sine of theta over 2. That's the sine of theta divided by 2. That's not the same thing as the sine of theta over 2. So let's try some of these. What is the sine of theta over 2? I don't know. I didn't memorize it. So sine of theta over 2 is square root of 1 minus cosine theta over 2. So the sine of theta over 2 is the square root of 1 minus cosine theta all over 2. Well, what is the cosine of theta? Cosine of theta is adjacent over hypotenuse. So the cosine of theta is 4/5. So it says I should take the square root of 1 minus 4/5 and then divided by 2. Well, 1 minus 4/5 is 1/5, right? 5/5 minus 4/5 is 1/5. So I get the square root of 1/5 divided by 2, which is the square root of 1/10, which I can take the square root of the top, square root of the bottom, and I get 1 over the square root of 10. If I rationalize my denominator, square root of 10 over 10. All of these are going to be positive because look at my angle. My angle is an acute angle. If I take the angle and divide it in half, it's still going to be an acute angle. So these are kind of boring in the sense I'm not going to put the plus minuses here because they're all going to be pluses. All right, let's look at the formula for cosine. Cosine of theta over 2. Look, it's the same thing except there's a plus instead of a minus. So I'm going to get square root of 1 plus cosine theta over 2. So cosine theta is 4/5. So I'm going to get the square root of 1 plus 4/5 over 2. Well, if 1 is 5/5, 5/5 plus 4/5 is 9/5. Over 2 is the square root of 9/10. So I can break this up. Square root of 9, square root of 10. Square root of 9 is exactly 3. So I get 3 over root 10, which, I don't know, it's not a terrible way to represent the answer. But if somebody says you have to rationalize the denominator, then we rationalize the denominator, and we get 3 square root of 10 over 10. Right, if you want the tangent of alpha over 2, you could knock through that formula, but you realize that I already have the sine and the cosine, so why not just divide them, and I'll get the tangent. So, since we're this close to the end, so tan of theta over 2 will be sine over cosine. So the sine is 1 over root 10. The cosine is 3 over root 10. And look what happens. If I multiply top and bottom by the square root of 10, I get 1/3. And there's my answer. Right. So we don't use these half-angle formulas all that much, but it is nice to know they're there, and if we need to use them to either manipulate an equation, show an identity is true, or find a value, like in this case, we're able to do that. All right, that's it.